Welcome back! Today we're going to continue our conversation about EMC, and it's a very exciting day because I've got a bunch of actual products in my car, and this afternoon I'm going to drive to Chandler's Ford in Hampshire, and we're gonna go inside one of the real EMC test labs and do some tests. We're going to begin with radiated emission scanning for a few products, and then we're gonna move on to conducted emissions and electrostatic discharge. This is not going to be a complete set of tests for a certification for, let's say, a CE logo, because this is just going to give us an overview of potential faults that we may encounter in a system, or as we say, it's pre-compliance testing, which means it's a testing that's done before certification. So this is our setup for radiated emissions, and we have on the table a device under test with cables connected so that it simulates the real-time operating condition that you will experience in the actual environment. And the antenna is switching from horizontal to vertical orientation, and the table rotates 360 degrees while the scan is performed. So this is essentially the way we do it in anechoic chamber, and this is a fully anechoic chamber, so the difference is that there is no metal plate on the floor, which would be the case with a semi-anechoic chamber. So this is actually faster and easier to work with.
It's going to go for a pre-compliance scan. Following for a little routine around here. So that turntable, you set it up. Let's connect to the antenna cable. These are the angles. It's going down in 45-degree steps. It will start from 0 degrees, facing in front of the unit. This is the instantaneous scan it's doing now. It's a peak trace versus a quasi-peak limit. The antenna horizontal polarization. It will then move the antenna to vertical. It repeats that, and this is building up a composite pattern of each trace. So effectively, if you rotate an angle or change the antenna slightly higher, you'll see it here. So it goes through, this is a combination of 2 polarizations, 8 positions, 16 scans that we do. This is what takes about 10 minutes, and it will eventually build up this composite trace. You can see here you've got a limit line. This is slightly curved down here. This is because we're in a fully anechoic room, not a semi-anechoic room, but it's the same, just we don't have a ground reflection. Once this is finished at 10 minutes, we can look at various peaks, and we can get those to make a final measurement. Now, you see that's over the line. That doesn't necessarily mean it's a failure, because that is a peak trace. This is a quasi-peak limit. We'd have to make a final measurement on these individually.
Later on.
Yeah, and it takes 3 or 4 minutes for each one to do that. And it would then go around in 360 degrees, find the worst case angle, and then switch on a quasi-peak detector for 20 seconds and make a measurement and plot a little blue diamond, and it generates a table of values, and it will tell us then the exact margin in dB relative to the limit, either above or below, and that is the result, not this apparently being over. If we look at the signal at 439, I can't see a steady state CW signal, so what I mean is a nice pure sine wave. If that had been the case, we'd say it's going to fail, because a steady state wave, it doesn't really change. It doesn't matter how even if you average it or RMS average, it's going to be the same value. Whereas you can see a peak here, you can see this other energy, the nature of that signal, this will drop. The question we don't know is by how much it's going to drop.
So as you can see, based on the results we obtained from radiated emission scanning, we did not achieve a pass today, and that is because we had a slight issue on the back of the console, which has to do with the grounding of the back plate of the display. Also, the hinges on the back of the console are made of plastic and not metal, and this is another factor why we're not getting a continuity test. We've been able to come to this conclusion by disconnecting different parts of the system one at a time. So we turned off one display, then we turned off another display, and we noticed quite significant decrease in emissions, so that must mean that this is the source of emissions really. Now our next step is conducted emissions testing, and conducted emissions is testing of the power supply and emissions it generates back into the mains. Now our console has power supply modules that are coming from a company called Minwell and which were not designed by us. However, even though they passed all the standards on their own, we still expect that they may fail the conducted emissions test simply because when they were tested against the resistive load, meaning that the situation may change under the real load, and also the tests that have been done by the manufacturer by no means can take into account the potential emissions that may come from our console itself and all the digital circuitry that it contains. So the point is that it is still necessary to test for conducted emissions even if your power supply comes from a third-party manufacturer.
This is a setup for conducted emissions.
So we can see that in this case, actually we've been able to achieve a solid pass, and we have simulated the worst case operational conditions where we have another device connected on a power over Ethernet line, so it's powered from the console. Finally, we're going to perform some electrostatic discharge testing. We're not going to perform it on the Epic console because it can be quite destructive to it and we don't have too many of them around. We're gonna have to do it later on for certification, but because we already know that we failed the radiated emissions and we're not going to get full certification this time anyway, we're just not gonna do this test. However, we're gonna do it for the Infinity control panel. And the purpose of electrostatic discharge test is to simulate the kind of effect that a human might induce on an electronic component. Basically, when you walk around on a carpet and you touch something and it does a zap, then this is kind of called the electrostatic discharge. So we're trying to simulate that. And we do that with a funny looking ESD gun, and this sort of device basically produces electrostatic discharge at multiple voltage levels, which can be 4 kilovolt, 8 kilovolt, and I think even 16 kilovolt. But the latter is reserved for kind of medical applications and maybe military. But in consumer electronics, we usually aim at 4 kilovolt contact discharge and 8 kilovolt air discharge. And the difference between contact and air discharge is that contact discharge is applied at the points where you have exposed conductors, such as connectors, displays and so on, whereas the air discharge is going to be applied at all places where you don't have exposed conductors. For example, if you have a plastic case, you're gonna apply air discharge all around it and see if it zaps at any specific point. In an ideal world, it shouldn't, and this is the sort of thing you would hope for. But if it does zap, it should get dissipated over the entire chassis and into the ground plane and not cause any malfunction to the device. Electrostatic discharge test does not have any metric, and the result is either a pass or a failure. However, there are different degrees of failure. The failure can be either a complete failure, where the device stopped functioning or simply broke down, or it can be an intermediate failure where the device continued working, however changed one of its states. And this can be acceptable for consumer electronics. Obviously, that would not be acceptable for medical instruments and devices like that, so it does depend based on the application.
Is this metal?
Yes,
Yeah,
yes.
it's all metal,
It's
yeah.
aluminium.
It's not discharging through there, but okay.
And you're swapping polarity around
Yes.
them.
Yeah, I do the same points before I turn it over. Actually, I could do the air on this side as well. I'll do everything on this side first. These are always really tricky to test because we need to get the probe near without. Sometimes it arcs off to the edge.
Yeah. So far, so good.
Being tested.
Yeah.
And so the levels, I mean, the main thing is it's the standard levels: 4 kV
Yeah.
air. It's like 4 kV contact, 8 kV air. And actually, that's basically when you see this pointy one. That's
contact.
That's the contact. Yeah.
Yeah. Doesn't have a graph or anything. Even when you like pass it on a certification report, it's only just literally a picture of the setup.
Yes. Yeah.
You know, and
We usually
passed
we take a
oil
number of
field.
photos. Yeah, we annotate the photos.
Yeah, yeah.
With each point. The photos are annotated with a series of arrows.
But yeah, but it doesn't have any degrees of failure. It's just like fail or pass, and that's it.
I mean, what the report is, when we do a forward test, the report shows all the points that
All
were
the
tested.
points where it's been applied. Yeah.
We don't generally do centre pins.
Okay.
And they are, you can see they're sort of recessed.
Yeah.
Lines there.
Do it on USB. Have you done it on USB?
This one here, yeah, the outer.
No, this one.
Oh, sorry, yeah, I did the centre bit there.
Oh, did you? Okay, sorry.
Yeah, I want to change polarity. And occasionally, where you've got a product that's got a sensitive connector,
Yeah.
and if it's particularly exposed, you'll be able to touch it. We've had some customers, some products, they'll fit a plastic cover over, so that's what's fitted. We then apply the air discharge to the cover. That offers you a protection. You know, it's really simulating what could happen if somebody touched that. So.
Yeah. In our case, we did not see any failures or change of states when it comes to the Infinity control panel, so it passed with flying colors. As we were working in the EMC test lab, we also saw those devices doing surge immunity test, which is another mandatory test under CE regulations. And what this test does, it introduces spikes on the power supply over a continuous period of time. So this test can take over 4 hours usually. So this is why it's just left there to its own and it's just sitting there for 4 hours. Obviously we're not doing it while we're in a chamber, but we may send back our equipment and get it done, but we're just not gonna sit there and look at it for 4 hours, if it makes sense.
Yeah, its surge immunity is also in like 61000 specs somewhere. It's one of the tests that's quite... I mean, strictly speaking, we should do it for Epic. But it takes, yeah, if it takes 4 hours, maybe not today. This is just someone else's equipment. So it generates pulses on phases. So some pulses on positive, some pulses on neutral, and it's measuring the disturbance. So like if it's able to disturb the equipment, something like that. Yeah, it creates fault condition, kind of, and measures how the equipment deals with it.
So in this video, I try to give you a brief overview of a typical visit to EMC testing lab and the tests that we usually do. So hopefully you've been able to gain some practical knowledge from this, and you know now what to expect when you do this kind of thing. And I do remind you that you must do it in order to comply with FCC and CE regulations for US and European markets. So typically I would recommend to do pre-compliant testing a while before the release of the product to avoid the mad rush just before the release, when you release your product but it is not passing EMC, so you can't sell it, so you're delaying this and delaying that, and everyone's really upset. It's just best for everybody to schedule it well in advance after you've done your first prototype, and then you'll know exactly if your product has any issues or if it doesn't, and then you can self-certify or certify through a third party such as Intertech or Hersley EMC. So I hope you found this video useful. Please like and subscribe for content just like this, and I'll see you very soon in the next one.